depends upon, okay, let's assume that depends upon the quality of the habitat, which might be the gradient, it might be the substrate size, it might be the temperature, might be fine sediments, and that in poor habitat, egg survival rate is really low, that's the red line, and as the habitat gets better by whatever dimension, egg survival rate goes up. And then that horizontal black line represents the replacement level, that if you can't get that egg survival, the life history of the salmon is such that it won't replace itself. So in the absence of fishing, you would expect any habitat that had an egg survival rate above the red line, above the black line, would have fish in it. But as you increased harvest, that replacement line would rise. And then if you want to maximize the yield across that watershed, you would have to look at how much habitat, the blue line, there is in different habitat qualities. And almost certainly some of the habitats that would be there in the absence of fishing would no longer support fish. Okay, next I want to jump to another paper coming out of the research station at Nanaimo, although it also included the lead author, Jerry Pollack, was actually at the University of Washington for much of his career. And they did followed up on these issues, but I wanted to highlight that what I've got there in red, that they're thinking about both wild and enhanced fish stocks. Characteristic of enhanced fish stocks, primarily through hatcheries, is to have a higher overall life history survival rate, which means they can support a higher rate of exploitation. And this was just at a time that there was a boom in hatchery production in the Pacific Northwest, primarily of Chinook, coho, and steelhead. And so what they warned is that the establishment of a new and highly productive hatchery stock might be responsible for an increase in the rate of exploitation. And that certainly happened. And that resulted in elimination of the less productive existing stocks harvested in the common fishery. And that was certainly one of the consequences of the expansion of hatchery programs back in the 1960s, 70s, and 80s. Okay, I just have to mention that my first fisheries paper, as Carl mentioned, I started out in the small mammal business, was on this topic, the optimal exploitation of multiple stocks by a common fishery. And this was really just the application of what at the time to us was a new technology, dynamic programming, to solve the optimal exploitation of a range of mixed stocks. Okay, now I want to jump ahead to some more recent work. This is from the Worm et al. 2009 paper. And this is a figure that Beth Fulton put together from a range of ecosystem models. And it's really just a cartoon of how you expect a mix of stocks to behave. And the blue line is the total yield from the mix of stocks, long-term sustainable yield. And like a single stock, the blue line rises as you raise exploitation rate and then declines as you start fishing too hard. And the green line is the total abundance of the mix of stocks, and it declines continuously as you increase the exploitation rate. And actually, both of those are very similar to what you see with a single species population dynamics model. But the orange line is the number of species that would be called collapsed. As I remember, I think it was 10% of their unfished biomass. And what you see is that if you were to maximize the total yield from this mix with an exploitation rate a little above 40%, you would have about 40% of your stocks collapsed. So that would be maybe not extinct, but at levels that would be causing a fair amount of conservation concern. And certainly in the US system, it would be illegal to fish that hard and cause them to be at that low abundance. And in fact, if you want to not have any stocks collapse, which is essentially a US legal requirement, you would have to give up about half of the catch. Okay. So there are different approaches to managing mixed stock fisheries. And what the US has adopted is weak stock management. That is, we are required by law to maintain even the least productive species at or above the level that would produce maximum sustainable yield. Now, an alternative is to maximize the sustainable yield of the mix of the stocks, either maximize yield or value. And you could add a lot of constraints to that. And one way to do that is with mixed stock F policies that we're going to get into a little bit later. So a mixed stock F policy for this cartoon that Beth Fulton put together would be to fish maybe at 22%, and you would still get 90% of the yield, and you would dramatically reduce the number of stocks that are collapsed, but you still would have some collapsed stocks. So now I want to switch gears and talk specifically about a fishery that I and Kristen have both worked on. And this is a paper that we did about 8 years ago, looking at this highly mixed stock fishery off the west coast of California. It had, there's on the order of 100 species have been caught by the fishery. This is a bottom trawl, a little bit midwater, but mostly bottom trawl fishery. And it's interesting. Kristen will talk more about it, but it was classified as a fisheries disaster about 1995 or so. The upper left panel is the total demersal biomass. And you see, going back to 1950, it was running about 3 million tons. The abundance declined in through the 1990s, turned around about 2000, and dropped to about half of what it was in 1950, when it was largely unexploited. If you look in panel B, that is, the dots are the total catch, rising from about 20,000 tons to over 100,000 tons for a few years, and now back down to about 20,000 tons. The gray line in that panel B is the harvest rate, which is the right-hand axis. And you see it was about 1% of the demersal biomass was being taken. It rose as high as 5%, and it's now down about 1%. So to my knowledge, this is probably the most lightly exploited major industrial groundfish fishery in the world, taking 1% of the biomass every year. Panel C shows the net surplus production from the ecosystem over time. And that is just the difference in biomass plus whatever catch was taken out. So if the biomass is staying steady, the net production is the catch. If the biomass was increasing, then the net production is the catch plus how much it increased. And what you see is that as the fishery developed, the surplus production increased, and it reached a peak in the 90s and 2000s. It never declined. So from the perspective of maximum sustainable yield, that system was never overfished. Although it was, and many people considered it a collapsed ecosystem, and Kristen will talk about that. The lower right-hand panel is just plotting the relationship between the surplus production and the demersal biomass. And you see that as the stock was fished down, surplus production increased, and we never got to the point of overfishing and seeing the total biomass, the total surplus production decline. So now I'm going to switch over, and Kristen is going to go take us through the next part.
Thanks, Ray. Perfect there. I'd like to first outline some of the major events in the history of this fishery, starting in 1996, when the Magnuson-Stevens Act, the governing fisheries legislation in the U.S., was reauthorized, mandating overfished stocks be rebuilt within 10 years or 3 generations. Now for stocks where this is biologically impossible, often seen with are long-lived rockfishes. The timeline is set by the time to rebuild in the absence of fishing plus 1 mean generation time. Following the reauthorization, the West Coast had 10 groundfish stocks declared overfished in the late 90s and early 2000s, which was followed by the formal adoption and implementation of rebuilding plans. In order to adhere to the strict timeline necessary to meet rebuilding requirements, total allowable catches were dramatically reduced. The TAC for some species was reduced by as much as 80% within 2 years. The seemingly overnight shift from target species to now constraining species meant the industry could no longer prosecute a directed rockfish fishery, further leading to the loss of markets and processing infrastructure. And as an example, in the late 90s, there were 113 first receivers up and down the coast. And as of 2011, that number was down to just 40. There was a lot of consolidation and overall operations going out of business in both the processing and harvesting sectors. And to highlight just how constraining some of the rebuilding catch limits were, I want to point out probably the most extreme example in yellow eye rockfish, where some vessels were allocated just 1 pound of yellow eye quota a year. And in the event they exceeded their 1 pound and could not find additional quota to lease, they were required to stop fishing for the remainder of the season. Next slide. The implications of the rebuilding plans were costly, but we do see several key management actions that took place following those overfish declarations. In 2003, the rockfish conservation area was implemented, closing areas coastwide to demersal trawling to protect these rebuilding rockfishes. In 2011, the fishery management plan was amended, creating the catch share program, allocating individual transferable quotas, and further requiring 100% observer coverage. Around the same time, we see the formation of cooperatives, primarily in the whiting sectors, but here the fleets use information sharing, real-time monitoring, hotspot closures, excluders, and a suite of other tools to minimize encounters with non-target species. Next slide. Throughout the various management action and efforts to rebuild overfished stocks, we observe utilization, or the ratio between catch and TAC, decline. And we further recognize that this issue of underutilization was challenging mixed stock fisheries across the US. As an example here, we have the West Coast non-whiting groundfish on the left and the Gulf of Alaska groundfish fishery on the right. Now the left-hand y-axis for both panels has total catch and TAC shown by their respective dotted and solid black lines. The y-axis on the right is the proportion utilized, highlighted in red. And focusing in on the West Coast, we see utilization decline from 80% in the early 90s to 20% in 2017. So in this paper, we interviewed fishery stakeholders across the two regions in an effort to better understand what's driving catch to be so much lower than TACs. Next slide. A few themes emerged from both regions, the first being that catch is often constrained by co-occurring species. The constraining species differed across the regions, but largely as a reflection of the two management frameworks at play. In the Gulf of Alaska, salmon and halibut are regarded as prohibited species catch in the trawl fishery. Thus, the hard caps on salmon and halibut can inhibit the fleet's ability to fully utilize their target species TAC. And as I previously described, the West Coast is under a catch share program with allocated ITQs. And here the constraining species are those for which quota is lowest relative to a harvester's quota portfolio. And the term choke species is commonly used here to refer to these low quota species. Stakeholders also reported that insufficient market demand was constraining. In both regions, utilization of flatfish suffered from poor demand. And then looking to the West Coast, participants noted challenges selling fish that hadn't been targeted in 17 years due to rebuilding plans. and the high lease prices of these quota stocks on the West Coast can help us identify some of the choke species that are constraining utilization. Next slide. The ratio between lease and ex-vessel prices here demonstrates how harvesters are paying far more to lease these stocks than they're actually worth, at least in terms of ex-vessel value. We can infer that fishermen are not leasing these choke species to go out and target them, but rather they're leasing fish to fund their target fisheries and cover incidental catches. And taking a deeper look at the West Coast, we saw many of the factors contributing to the current underutilization point back to the rebuilding plans. And this prompts our current work. If you'll move to the next slide. As of 2019, 9 of the 10 previously declared overfished stocks were assessed to be rebuilt. Knowing what we know now, Ray and I wanted to look at what might have happened if alternative rebuilding policies had been adopted. To do this, we took the biological parameters and recruitment deviations estimated in the most recent assessment to model retrospective projections starting in 1995. We chose the year 1995 as that was the year prior to the reauthorization of the Magnuson. And then we looked at projection output of spawning biomass and catch under alternative scenarios. So I'd like to first walk through our results for canary rockfish, directing your attention to the panel on the right here with stock depletion or the spawning biomass relative to the unfished level. The solid black line is the stock trajectory that comes from the 2015 assessment. That vertical line intercepting at the year 2000 is the year the stock was declared overfished. The horizontal gray line, which we'll highlight here in purple, I believe, is the management target. The Pacific Fishery Management Council uses proxies for BMSY, and for rockfish, the target is set at 40% of the unfished spawning biomass. Now, the small dotted gray line, which we'll highlight in blue, is the spawning biomass corresponding to MSY. And it's important to differentiate these two lines here, as the rebuilding plans and the reference points used for management are the default proxy for SBMSY, that purple line. The assessment still estimates a true MSY and corresponding FMSY and SBMSY, which we've shown here in blue. And then finally, this larger dashed gray line is the overfished threshold, which for rockfish is a default threshold at 25% of the unfished level. It is interesting to note here that the SBMSY, the blue line, is actually a lot closer to the overfished threshold than it is to its proxy. Now the panel on the right is catch scaled to MSY. This horizontal line here, intercepting at 1 is MSY, and we've gone ahead and shaded years where catch was above that, just to highlight that canary had a long history where fishing was really hard relative to MSY levels. And then in 2000, the stock was declared overfished, and we see catch fall nearly to 0. Next slide. And so we looked at what might have happened if a rebuilding plan had not been implemented, and instead the fishing mortality rate in 1995 was held constant. The results of this projection are shown here in green. Spawning biomass on the left is projected to rebuild, actually surpassing the management target, that gray line. However, the trade-off is it rebuilds at a much slower rate compared to what actually happened, that black line there. However, in return, on the right, you see the projection of much higher yield and actually up, close to MSY. Next slide. We look at, next we looked at an FMSY scenario. So what would have happened if we reduced fishing mortality to the rate that produces maximum sustainable yield? This is shown in red. And the rate of rebuilding on the left is lower in the stock. In this scenario, does not quite meet the management target necessary to be declared rebuilt. But again, you see the trade-off of greater opportunity for catches. And finally, the next slide, we modeled a 0.8 FMSY, so a slight reduction. And the results here are similar to that of the other two alternatives. Next slide, please. We did this for 13 different stocks, and the stock size projections for each are shown on the slide here. Now, 8 of these were stocks previously declared overfished, and that is denoted with that vertical black line. And 5 of them were abundant stocks for which catch was constrained due to rebuilding. And if you try and follow that green line across the panels, we see that if fishing had continued as it was in 1995, the projections infer that only yellow-eye rockfish would have actually collapsed. The remaining 7 previously overfished stocks would have either rebuilt on their own, or their biomass is projected to at least remain constant. The same is true under the FMSY and 0.8 FMSY policies, except that we begin to see yellow-eye rockfish rebuild. If you'll move to the next slide. And as we saw with that first canary example, projected catch under the 3 alternative scenarios is substantially greater than what actually occurred under the adopted rebuilding plans. Next slide here. We took the catch projections along with the annual ex-vessel values for each stock to calculate the total ex-vessel revenue under each scenario, and compared this to what actually happened under the fishery's actual value to calculate foregone revenue. So under these alternative rebuilding scenarios, using current information, the projections infer the fishery could have attained an additional $610 million to $886 million in ex-vessel revenue over the last 25 years. If you'll move to the next slide. The National Research Council did a study on U.S. rebuilding plans in 2014. This quote comes from their report, where they concluded rebuilding plans that focus more on meeting selected fishing mortality targets than on exact schedules for attaining biomass targets may be more robust to assessment uncertainties, natural variability, and ecosystem considerations, and may have lower social and economic impact. Ultimately, our results, or the results in this analysis, support that of the NRC, demonstrating how costly rebuilding plans based on strict timelines can be, and how plans based on fishing mortality targets may allow stocks to still rebuild while seeing less trade-offs in food production and profitability. And with that, I'll turn it back over to Ray.
Okay, thanks, Kristen. Yeah, so sort of the bottom line lesson from the US West Coast is that if your only objective is to rebuild stocks, then the current US approach to rebuilding is great, but it has great costs in terms of food production, social, and economic costs, which are in fact what we're really trying to achieve with our fisheries management system. Now I want to switch gears and move to some even more mixed stock fisheries, which are, I'll sort of generally call them mixed stock tropical fisheries. So if you remember that very first slide of the distribution of stock assessments, the big gaps were in largely South and Southeast Asia. And in those places, almost all of the fisheries, or certainly a very high proportion of them, are very mixed stock. And so this is data from a paper by Tim McClanahan, who works for the Wildlife Conservation Society, and was part of the working group that Boris Worm and I put together back in 2007. And I think the most surprised I've ever seen anyone in my life is when in our first meeting, Tim McClanahan got up and said, okay, I work on small scale fisheries in Kenya. And there, the harder you fish, the more you catch. And Boris was just totally unbelieving. You know, Boris is used to, and in fact, I was used to sort of temperate fisheries, where if you fish too hard, you get less fish. That's where the whole concept of overfishing really originated. And Tim said, no, in the fisheries he's worked on, they've never seen a place where the catch declined because you were fishing too hard. But what you do see is very substantial ecosystem changes. So in this graph, the open triangle diamonds are the total catch. And this is basically measuring fishing effort as the number of fishermen fishing days per linear kilometer of coastline. And what you see is it goes up as fishing effort goes up and then essentially flattens off. But if you look at piscivorous fish or carnivores, those are the black squares, they basically disappear at high fishing levels, whereas herbivorous fish, the circles and octopus, the open triangles are all increasing as you fish harder. So what's happened, and there are other data sources that show the same thing, is that under intense fishing pressure, long-lived species decline and often disappear. Short-lived species become more productive as their predators are depleted. And we've seen this empirically in the McClanahan data. But just want to remind, this is going back to what Ricker said, if a common fishery cannot be avoided, the achievement of maximum average yield may find one of two originally equal stocks as abundant or even more abundant than before the fishery began, while the other may persist at low levels or even be exterminated completely. Now, Willy and a number of his collaborators really showed the same thing. So they, using it, Willy can correct me at the end, but I think they were all EcoPath or EcoSim models, comparing different time periods going back 100 years. It suggested our results predicted that the biomass of predatory fish in the world, and I think that was trophic level 3.5 and above, has declined by about 2/3 over the last 100 years. Now, I have to say, when this paper came out, I said to many of my colleagues, I said, this is the most optimistic paper on fisheries I've seen in a long time, because that kind of decline is exactly what you would do if you were trying to maximize sustainable yield. That is, reduce the abundance of those predatory fish to 30 to 40% of their unfished biomass. But more interestingly, what they found is this indicated that the biomass of prey fish, trophic level 2 to 3, had been increasing over time by about 80.85% a year. So over a 100-year time span, this corresponds to a 133% increase, suggesting that there are now twice as many prey fish as the global ocean as there were a century ago. So that's why I said, this is really quite optimistic, because at the time I was involved, and still am, Carl is, in a lot of debates about fishing forage fish, and should we protect the forage fish of the ocean? What this is basically suggesting is the oceans are full of forage fish. But even more interesting is, because trophic levels are more abundant, remember the pyramid of biomass and energy flow, this means there would actually be more tons of fish in the ocean now than 100 years ago. And that's just not quite this popular image of the oceans being emptied of fish. But of course, these are different fish than we would have seen 100 years ago. So now I want to jump to another more recent paper that came out of a group at UC Santa Barbara, led by Cody Suzwalski, looking at the fishery in the Yellow Sea of China. The East China Sea. And they used a size-based model to what they felt was a pretty comfortable fit to the history of catch in that system. Again, what they found is the larger long-lived species either tended to disappear, or in this case, they often change their life history. So if you look at this upper right-hand panel, that's a fish called the hairtail. The hairtail has gone from maturing at 3 or 4 years of age to basically being an annual species, and it still maintains a pretty high biomass and a pretty high catch. I think it may still be over 1 million tons a year, which, let's just say by Canadian standards, is a very big fishery. So what they conclude is, our results suggest that implementing single species management in currently lightly managed and highly exploited multi-species fisheries, now that accounts for most of Southeast Asia, which is a large fraction of global catch, this may result in a decrease in global catch. So the kind of management system that we've put in place in the US and in Canada and in Europe, if we said, oh no, you've got to rebuild those long-lived species, their estimate is that it would result in a major decrease in the total production of food from those systems. So conclusions regarding highly mixed tropical fisheries is that total food production and employment may be maximized at high fishing mortality rates, but it certainly comes at a high ecosystem cost. You end up with a very different ecosystem and one that's very dependent on a smaller number of species. It's probably economically inefficient. These fisheries are probably overcapitalized quite a bit, and it has very high greenhouse gas footprints. So I want to talk in closing about ways to sort of solve these problems. And how can we get more food from the ocean with fewer problems? One is moving away from weak stock management to ecosystem-based management. That is setting what are our standards with respect to the ecosystem. It seems rather silly to say we have to rebuild every stock to the MSY level when the MSY level is a concept of maximum yield, and you can't get maximum yield from every species. Very common actions that have been implemented, and we can adjust the selectivity of fishing gear. We can selectively close areas, as was done in the rockfish conservation areas, and I should say that a second part of Kristen's master's thesis is really looking at whether those closed areas were very effective when combined with other fisheries management measures. There's lots of work going on gear modification, trying to modify gear to more selectively target species and less harvest other species. I'll talk about that a bit more. There's been a long history of using fishing modifications to reduce the bycatch of non-target species. So the tuna back down procedure was quite effective at reducing porpoise bycatch. Dolphin bycatch, or are they dolphins or porpoises? I always forget. Longline fisheries have a lot of interactions with marine birds. Those can be dramatically reduced by setting the gear at night. And then there have been a lot of work on fishing incentive schemes, such as real-time closures and fleet agreed no fishing areas. Again, all around trying to avoid catching constraining species. More techniques is information sharing among vessels through co-ops. And I should say that Kristen's job instead, in addition to being a graduate student, is she is the manager of one of these co-ops, and they get daily reports on bycatch rates, and when they start approaching concern, then Kristen has the legal authority to close areas to fishing to her fishing fleet. These are legal authorities by group agreement, not by governmental regulation. The incentive systems for individual vessels, these are individual vessel quotas, very common. British Columbia groundfish fleet certainly uses those. And then there's a lot more work going on technology to make gears more selective. So one of these technologies is adding cameras to fishing gear. So in the old days, if a fisherman wanted to avoid catching species that he didn't have quota for or didn't want to catch for various reasons, they could put their net down, maybe spend 5 minutes in the bottom, come up and look and see what they have, and if it's the right mix, then go fish that site. Now they can put a net on the camera and sit there in the wheelhouse and see what they're actually catching, whether they're damaging their gear, etc. Now, this is really, I think, a very cool area. There's more and more cameras being used, and they can pull the net if the wrong species being caught. But there are also a lot of experimentation going on now with electronically activated excluders. Think of it as just opening a door and kicking the fish out, that if the skipper sees the wrong fish coming in the net, he simply opens the door. And I know of several research groups that are now trying to automate the whole process, where you have artificial intelligence software viewing the camera real time and opening and closing the excluders as fish come in. And so I think within 10 years, we'll probably see this technology start to be quite a bit more widespread. So let me conclude by saying mixed stock fisheries are perhaps the major challenge to fisheries. That, as I started, we know how to manage single stock fisheries. We have bycatch concerns for threatened species. We have ecosystem impact of non-selective fishing. And we have all this lost food production from constraints imposed by bycatch. But different countries are going to make different choices in the trade-off between yield and ecosystem changes from fisheries. That the US and Canada have all sorts of laws that are pushing us towards foregoing yield in order to have less ecosystem impact. Myanmar, China, Thailand, Indonesia, and China will probably make different national choices along those lines. But one thing that I think that even in countries like the US, we need to remember is there's a broader trade-off. So I know there is a very big movement to simply ban trawling, which produces about 20% of global fish catch. If we were to do that and reduce global fish catch by about 20%, that animal protein would almost certainly be made up by other forms of protein production, which is basically livestock. And right now, almost all increase in livestock production is coming by producing either livestock directly or feed for livestock by chopping down tropical rainforests. And so that when we think about the trade-off between ecosystem impacts in the marine world and and food production in the marine world, we have to always think through, okay, if we choose to be very cautious in fishing and give up a lot of catch in order to protect our marine ecosystems, what are going to be the terrestrial consequences? So thanks very much. So back to Murdoch, is that right?
Yep. Thanks very much, Ray and Kristen. Very great talks, and I'd like to open it up. We've got about 10 minutes for questions, and so I'd just like to open it up for questions, and Billy can help me manage the questions. So
yeah, and we can start with Jimmy and Ellie. You can just unmute yourself. You're still there.
Hey, can you hear me?
Yeah.
No, I was just on that
Morning,
early
Jimmy.
slide. Eh?
Morning, Jimmy.
Go ahead, Jim.
Hi, Carl. No, I was on the early slide, and you probably say it in the paper, which I haven't read, but the surplus production one, just that, the pattern of increased surplus production with fishing. I just wondered how much of that is due to the fact that probably most of those production values early in the time series are from models, which are starting from some initial conditions where you wouldn't expect surplus production. So I don't think the value of the measure is the same across that scale of time series. Does that make sense?
Well, yeah, but yes, because there were no recruitment deviates estimated early on. But I think that the pattern that as the stock fished down, the surplus production increased is pretty unavoidable. You just, at low fishing rates, you just don't have much surplus production.
It's almost by definition, though, right? And I just wonder if there's a better way to scale that or measure it. Just thinking out loud.
Well, you could, over the period where there's surveys, you could actually go directly from the survey. And the stock assessments typically do have that kind of assumption built into them through the spawner recruit relationship. But you could just do it directly from surveys. And the places I've done it, you see more or less the same thing. I can send you the paper that does that for some individual species.
Well, this must have been a really boring talk because we don't have anyone lined up for questions.
Ah,
I got a
Yeah,
question. So it seems like that there are a lot of potential things that you've listed that could be considered to, say, get around impacting the weak stocks. But it seems like you're throwing in the sort of like a towel, or you're just giving up on this idea that we're stuck with weak stock management. I don't know if there's a role for academics to, like you said, okay, what about ecosystem management? Does that, it seems we're still under this constraint of weak stock management. Um, like some have advocated in some contexts, like with salmon, sustainable overfishing. We're stuck with like ESA and SARA south and north of the border. And it seems like it's really hard to get around that. There's a real bent in government just to go after those, like to manage strictly for those weak stocks and shut everything else down. We're faced with really big closures up here in Canada due to weak stock, or let's say stocks that have been designated as threatened and endangered, like salmon stocks. And it's really going to be devastating. It is being devastating to fisheries now. So perhaps there should be more, let's say, consideration of alternative models instead of total weak stock management. Perhaps considering, let's say, sustainable overfishing models. And you got to go back to, let's say, the legislation saying this is what's really killing us.
yeah, I don't know the Canadian situation very well, but in the US, there is actually within the Magnuson-Stevens Act, there is called the mixed stock exception. That is, you can do what you might call, something like the FMSY policy I showed, where you would have a small fraction of your stocks overfished. But none of our management councils have been willing to invoke it because they're terrified of being sued by NGOs. And I've sort of taken it as part of, that's why I put in those last slides, is the NGOs are incredibly marine focused, and they many of them are pushing everywhere to reduce the amount of fishing that goes on, but they don't realize the impact of that on global conservation, because every bit we reduce marine fish catch is putting more demand on terrestrial ecosystems. And certainly if you look at endangered species, that the marine system has many fewer. I think there is right now only 2 marine fish species that have ever gone extinct. That extinction rates in the ocean are much lower than they are on land, and the number of species threatened on land, particularly in tropical forests, is enormous. You can have a mixed species harvesting system that depletes species but doesn't let them get anywhere near what might be considered an endangered species level.
Ray, isn't part of the problem here the thing that you highlighted in that food for thought, that there's an apparent lack of understanding of what the term overfishing means, and a deliberate attempt in some cases to imply that overfishing means imminent extinction. And so there's been a fear even in the management community with managers who very often don't understand population dynamics very well, to think that if they're allowing technical overfishing from an MSY point of view, that means everything's going to disappear under their management. There's a horrific misunderstanding problem here about overfishing.
Oh yeah. And it certainly extends to a large portion of the people who work in various aspects of fisheries and fisheries management. So one of the things when we were, let me just go back to a Kobe plot here. Do I have a, Okay, let's take that Kobe plot. And during one of this working group that Boris and I organized, where if you go in the upper of where you get the fishing pressure greater than 1, Boris did not understand that that did not mean the stock is going to extinction. That I can't draw it here, but is my cursor visible on this thing?
Yes.
Yeah, barely.
So
Right.
there's essentially, if you're just above 1 on the fishing pressure, but at low biomass, the stocks are going to increase. That there's a whole range of fishing pressure greater than 1 where you have the stocks increasing or stable. And I would say that a small fraction of people outside those sort of versed in population dynamics really understand that there's a whole range of sustainable but subject to overfishing biomasses. And that's really what happens as you back off from the multi-species maximum yield to lower and lower pressure. You end up with stocks in that range, and they can still be, you know, that's the other thing, is if you look at the many of the fish species that are listed under the CITES, well, no, actually, I'm sorry, under the IUCN Red List. I mean, these are species for which there are millions of individuals and the populations have been increasing. Atlantic bluefin tuna, for instance. A very high portion of the fish species that are listed as threatened or endangered are, you know, by no sensible risk analysis would ever have classified them as in any possible danger of extinction. So there's that just permeates the, you know, the marine conservation perspective.
Okay, thank you. It's 10:30. I don't, Murdoch, can we take one more question?
Yeah, let's
fine.
take one more. Yeah.
Okay, the rare thing about this is from Tam Caritas, who for once is speechless. But he is asking, how resilient are your conclusions to potential substock structure? If you imagine that science provided us with information about substock structure for our traditional single stocks of the likes we already observe for Pacific salmon.
Oh God, it just makes things even worse. that
Typical
you know,
Tom.
that you know, probably everything we call a fish stock out there has multiple substocks, and that probably have differential productivities. And
Ray, before you finish answering that, let me point out here that Ray speaks some direct personal knowledge. He has a large field research program on sockeye salmon in Bristol Bay, studying exactly what he's talking about, this variability on fine scales and productivity.
well, and fine scale stock structure. I mean, we have morphologically different fish that anyone can pick up and identify as whether it's from spawning on a beach or spawning in a creek, that are spawning 20 meters apart. So you know, we don't have enough information to know really how different they are in productivity. But yeah, I mean you can't find more substock structure than you can with sockeye salmon, as far as I know. And actually, I wrote I wrote a paper, probably in the 1980s, showing that if there are different productivities of different substocks, but you manage them and assess them as a whole, one of the problems with that is that as you increase exploitation rate, the more productive stock tends to dominate, and over time you will start to think your stock is more productive but smaller, because you are increasingly fishing down the less productive substock and relying more on, so that substock structure introduces a bias in your estimate of what the stock productivity is. And I haven't seen anyone following that up much in recent years, but you could argue that is probably could be happening in quite a few marine stocks.
Okay, so thanks again, Ray and Kristen,
Okay.
for your talks, and thanks everybody for participating. Thanks for the questions. And I have recorded at least a partial. I started a bit late, so there's a recording of this, and I'm going to ask Ray if you could send us his slides as well. So thanks again.
Okay, will do.
And we'll
Thanks
see
for
you
the
again.
opportunity.
Yeah.
Thanks
Welcome.
much, guys. You both did a really great job as expected. Good eye, mate.
All right, we'll
Bye.
see you.
Thank you.
Yeah, bye-bye. Yeah, see you. Yeah.